So you like torque, huh? Well, great. We're going to take a small detour here, a small diversion, to look at more mathematics so that we can do more physics. In fact, that's the main reason to do mathematics, is so that you can do more physics. Sounds good. We're going to introduce the vector product or a cross product and relate that to torque. The truest way to represent torque is through a vector product, a cross product. We can define the torque vector as being defined to be the radius vector to a point crossed with the force that is acting at that point. And that is a vector product. It gives us a vector when it's done. The magnitude of this vector cross product is the magnitude of the first vector, r in this case, the magnitude of the second vector, f, which is the force, times the sine of the angle between their two directions. We would choose the smallest angle between those two vectors, and then the direction of this torque vector will be given by the right-hand rule, which we'll show you on the next screen. So the magnitude of any two vectors, cross product, A cross B is equal to C, and C is equal to A times B, sine of the angle between the two vectors. To calculate the direction, you would take your right hand, point your fingers in the direction of the first vector, in this case A, looking like something like that. Close your hand through the smallest angle possible towards the second vector, B. And then when you've done that along the plane of those two vectors, your thumb points in the direction of the cross product. So A and B actually being vectors would define a plane themselves, and your cross product thumb will always be perpendicular to the plane formed by A and B. In other words, C is going to be perpendicular to both A and perpendicular to B as well. Note by the right-hand rule that A cross B will be equal to a negative B cross A. For instance, if I had A like this and B like this, and I did that cross product, A cross B, I'd be pointing up. But if I have A here and B here, if I did B first and then close my hand toward A, I'd be pointing down 180 degrees opposite. So the magnitude would still be the same, A times B sine theta. So A cross B is equal to the negative of B cross A due to the reversal of direction. If A is parallel to B, then the angle between the two would be 0 degrees, sine of 0 is 0. Or if they were anti-parallel, the angle between them would be 180 degrees, sine of 180 is 0. So for parallel or anti-parallel vectors, the magnitude of the cross product is indeed 0. If A is perpendicular to B, then the angle between the two would be 90 degrees. Sine of 90 is 1. So the magnitude of the cross product between perpendicular vectors would be equal to A times B sine 90, which is 1, or just the magnitude of A times the magnitude of B. And finally, the distributive law is also valid for cross products. If I had A cross B plus C, I can distribute that operation, A cross B plus A cross C. And so that operation is distributed between the two vectors, and that is a valid law. Consider three unit vectors which by definition are mutually perpendicular. So I have these unit vectors I, J, and K specifying the x, y, and z directions respectively. If I had any unit vector cross with itself, I would have magnitude of 1, which is 1, times the magnitude of the other, 1, times the sine of 0 degrees, which would be 0. So any unit vector crossed with itself is going to be 0. I cross I, J cross J, or K cross K, 0. Any unit vector crossed with any other unit vector is going to be some form of the third unit vector. So I cross j is actually equal to k. If I think of I as the x direction this way, and j is the y direction this way, if I go I cross j, I'm pointing towards u, which is in the k direction. If I did negative j cross with I, I'm pointing in the k direction towards u. J cross k. If I did j cross k, I'm pointing in the I direction. Or if I did negative k cross j, I'm pointing in the I direction. K cross I. If I did k cross with I, I'm pointing j. If I did a negative I cross with k, I'm doing j. If it's hard to keep these straight, here's a mnemonic memory device to help you. IJK, IJK. If I use this device to the right, in other words, if I go I cross j, I end up with positive k. Or k cross I end up with positive j. Anything going to the right on this mnemonic device is going to give me a positive next vector. If I go to the left on this mnemonic device, say j cross I end up with a negative k, or I cross k is a negative j, and so forth. Anything going to the left on this mnemonic device is going to give me the third vector, which will be a negative vector of that sort. Finally, we can do the cross product or vector product by using linear algebra, or in other words, the determinant. A cross B is a determinant of this form, where I put my ijk vector in the first row, and then my coefficients of the first vector, ax, ay, az, in the second row, and my coefficients of the second vector, bx, by, bz, in the third row. I wish to solve this determinant, and that will be my cross product. The way I like to solve a 3 by 3 determinant is to repeat the first two columns, and then just do my 3 diagonals going down, add those together, subtract my 3 diagonals going up. So I would have I times AYBZ plus J times AZBX plus K times AXBY minus the other 3 diagonals. So I'm going to have minus BXAYK minus IBYAZ minus JAXBZ. Put all my I's together, all my K's together, all my J's together, and I get the cross product. Let's try this out. Two vectors lying in the xy plane are given by the equations a equal 2i plus 3j and b equal negative I plus 2j. Find a cross b. So here's a, 2i plus 3j. Here's b, negative I plus 2j. And I want to find a cross b. Now, right away, since a and b are in the xy plane, if I did my right-hand rule to that, pointing in the direction of a, close on b, then I'm pointing in positive c direction towards u. So I already know, before I even do this cross product, by the right-hand rule, that my answer is going to be something positive k. It's going to be perpendicular to the plane formed by the first two vectors. So I have a cross b is 2i plus 3j crossed with negative I plus 2j. The cross product is distributive, so I'm going to have a 2i crossed with a negative I and a 2i crossed with 2j. And for that matter, a 3j crossed with a negative I and a 3j crossed with 2j. So I have these 4 terms from this distributive property. I cross I is going to be 0, so I would have 2 times a negative 1 times 0. So this first term is 0. And way over here, I'm going to have 3 times 2. J cross j is 0, so that's going to be 0 as well. Now, j cross I is a negative k. So I'm going to have a negative 3 times a negative k, which is going to give me a positive 3k for that. And 2 times 2 is 4. I cross j is k. So I have a 3k plus a 4k, 7k. Okay? So that is our cross product for these two vectors. I could do the same thing using the determinant method. I'm going to fill my first row with ijk, my second row with the coefficients of vector A, which in this case would be 2, 3, and 0, no k component to A. And my last row is the coefficients of the vector B, negative 1, 2, and also 0. I wish to find the determinant of this. Well, I'm going to repeat my first two columns and do my diagonals. I'm going to have 0 plus 0 plus 2 times 2 times k, or 4k, minus negative 1 times 3 times k, so that's going to be a minus 3k, minus 0, minus 0. So I'm going to have 4k minus 3k, or 4k plus 3k, 7k. So that's how the determinant method would work for calculating the cross product. We're going to use these results to find the angle between A and B. We know that the magnitude of the cross product, A cross B, should equal the magnitude of A times the magnitude of B, sine of the angle between the two vectors. So, since the magnitude of A cross B we just found to be 7k is A cross B, so the magnitude of that is 7. The magnitude of A will be 2 squared plus 3 squared plus 0 squared, square root of 13. The magnitude of vector B will be negative 1 squared plus 2 squared plus 0 squared, square root of 5. Solving for theta, we have that theta is equal to the inverse sine of the magnitude of A cross B over the magnitude of A times the magnitude of B. That's the inverse sine of 7 over the square root of 13, square root of 5, gives us 60.2 degrees. So if you didn't have your trusty protractor in your pocket, you could calculate the angle between these two vectors by using the cross product. Well, we recall then that torque is truly a cross product between a vector r and a force applied at that point from some axis of rotation. The vector r is going radially outward, and the angle between them would be this angle between those vectors. So the magnitude of this torque would be the magnitude of r, the magnitude of the force, sine of the angle between their two directions. But if we found the line of action of that force and found the shortest distance to that line of action, we had defined that as the moment arm. And if we look at this triangle, with r being the hypotenuse of this right triangle, d is equal to r sine theta, or r sine phi if you actually look at this diagram here. So the torque is equal to the force times its moment arm, the shortest distance from the axis to the line of action of that force. If you can think that way, torques are going to be a lot easier for you. Okay, so why are we doing all this? If it were only about torques, then we'd just show you torques and then we'd go on. But we're going to be using these cross products for many other things. In particular, something like angular momentum. The angular momentum of a mass relative to an origin is equal to the cross product between a radial vector to a point and the momentum vector at that point. And it's represented by L, an L vector, which kind of looks, the L symbol kind of looks like an angle. So maybe that's why it represents angular momentum. So the angular momentum is equal to R cross P, which by the right-hand rule, if I were to point in the direction of R, going outward, and then in the direction of P, I'd be pointing my thumb into the page. So we'd be looking at the tail feathers of the arrows. It's going into the page. So in this case, the direction of this angular momentum vector is actually into the page. momentum is mass times velocity. So this would have magnitude equal to r times the magnitude of the momentum, p, sine theta, or mvr sine theta, where r is the radial distance to that point and v is the velocity of the mass. Note that if we were to define a shortest distance to the line of action of this momentum, which is h in this case, if I were to look at this triangle here, h would have to be equal to r sine theta. And that would be true no matter where on this line, as this mass is moving to the right, it goes, because even though the triangle starts stretching out, h will still be that same distance, shortest distance to the line of action of that momentum. So if I substitute in for r sine theta, h, my angular momentum equals mass times velocity times h. And as this is going to the right, that shortest distance h is a constant. So is the velocity, so is the mass. So even a mass moving in a straight line with constant linear momentum would have a constant angular momentum about some arbitrary point, some origin that's off the line of action. How about that? So linear motion like this can have constant angular momentum. A planet has angular momentum as it's going around the sun, equal to its linear momentum times the shortest distance to its line of action at that point, which would be the radius of its orbit. So the angular momentum of a planet at any particular moment would be equal to its mass times its linear velocity times its distance from the sun at that moment. And we'll see in the next video that this actually is a constant, or the angular momentum of a planet going around the sun is a constant. So that concludes our first lecture dealing with the mathematics we need and the introduction to angular